Hello, this is the third video in a three-part mini-series on understanding the formula in Veritasium's video on 100 riddles or prisoner's riddle. Now, in that video from Veritasium, the formula appears at 9:24 in the video, and it kind of flashes up and then goes away. But it's in regards to calculating the probability of observing a loop size of, say, k. And the first two videos I spent, trying to calculate these probabilities, understanding the formula. And so parts 1 and 2 are a must watch if you want to fully understand what we're doing here. And also, I think it'd be wise to rewatch his video, Derek's video. And the solution to this 100 prisoners riddle, if you haven't heard it, is so impressive, so amazing. So in section 1, there's two sections. This is the recursive formula that's in Veritasium's video at 9:24. And so it's a recursive formula, and here's the function for it. So let's run that code. And then what it does is, well, I'll just show you. It calculates the number of possible orderings or loops with a maximum of size 4. So this is n equals 100 and k equals 4. So you can even rewrite it like this if you want. N equals 40, k equals 24. And so look how fast it went through n equals 104. It went so fast, and you can do it for any n and any k. Now, when you start getting bigger k for, say, n equal 100, you see how it's slowing down just a little bit? I mean, because that's a big number that it's calculating. Now, here's the other thing. The machine that I'm doing this video on, it's actually the only machine that I have a good graphics card, but the actual processor is so darn slow, I can't really do much. So I would absolutely love it if someone would run this function on their fast machine, tell me how long it takes, and if it's so much faster than this machine, I'll probably go and just buy a new computer so I can have a better machine. Now, we can use this formula to calculate the whole distribution. Let's say we have n equals 35. And this is it. Boom. This is the probability distribution of all possible loop sizes when n is 35. And that's pretty cool. Now, again, it starts to slow down if you increase it too fast, or too much. And let's look at what 40 does. I don't really know. Notice that it's taking a little bit longer. Which, there it is. And so this is it. Given n equals 40, this is all the probabilities of the different loop sizes. And that's what that function gets us. Now, originally I was going to stop at that. But in making sure that I'm thinking about the probabilities correctly, I programmed some simple yet inefficient programs that I use to help me understand the problem. And they ended up being sort of cool problems, but it's really code to understand the underlying problem. So you can only do this for small n, well, at least on my machine. So what I wanted to do next is write some code that if I gave it a random sequence, then it would tell me how many loops we have. And that's what this does. So let's assume the boxes are in order from 1 to whatever n you pick. I'm going to do 100, so 1 to 100. Now you sprinkle down numbers into those 100 boxes, and then you go in and figure out how many loops you have. And that's what this program figures out. So the random sample piece takes a random sample and sprinkles down 100 numbers into those boxes. So it's assumed that box 1 has 18, box 2 has 93, and etc. But how many loops is this? So if you go from 18 to, and then follow it around, well, that's what this program does. So there's a loop of 52, 27, 10, 6, 4, and 1 in this sequence. And you can just keep rerunning that. Sprinkle down another set of 100 numbers, find the loops, and this is the distribution of the loop sizes. So from this you could find the maximum, of course, but then you also know the other different loop sizes. And that was pretty important to me when I was going through and calculating these by hand, making sure that I could figure it out. Then I thought, if for a given sequence of numbers, I could find the number of loops or the maximum loops. But then why don't I just generate all possible sequences of a number from 1 to n and then figure out the exact distribution? And so this piece of code here, the permutations, generates all permutations from the numbers that you provide. So 1 to 1, all permutations is 1. That's kind of silly. 1 to 2, there's 2 permutations, 1, 2, and then 2, 1. For 3, and these go up factorial, so they'll grow quite fast. So there's the 6 combinations, the 6 permutations of the numbers 1 to 3. 1 to 4 will have 24 different numbers, and etc. So I can feed this sequence into the function that I just created and find the exact number of loops. But then this is every loop possibility. So we can find the exact distributions. But it turns out this is only useful for small n. Okay, so let's do it of an n of 6. And so I generate all permutations of 6, and there's 720 of them. And by row, I calculate the loop sequences, but then I take the maximum, and then I save that. And so that's what this does. And then I table them. And so this is it. This is the exact distribution. There's 120 different orderings where the maximum loop is 6. 144 different orderings where the maximum loop is 5, and etc. And if you want to create a proportion table or prop table from that, you can. And this is 1 over 6, 1 over 5, 1 over 4, and then these are the much tougher ones to calculate. But then, as I'm doing this, I put 9 in here, and that's the example that I gave in parts 1 and 2. But it takes like 3 minutes to run, and that doesn't make a good video of just watching it run. And I couldn't quite match one of these numbers. And so I thought, well, I do have the exact loop sizes. So for n equals 6, I just run the sequence again, but don't take the maximum. I just save the loop distribution, and boom, it's there. So if I run 2, well, I'm not going to run it because it's too big. Now I can find it for, say, k equals 3. So here is, right here, there's 200 possibilities or 200 orderings where the maximum loop is 3. So I put k equals 3 here, and then find the loop sequences here, and this is it. So look at this, 40, 120, 40, that adds to the 200 that I had up here, right here. But these are the specific orderings. So there's 40 where the sequence is 3 and 3. There's 120 different ways that you can get a 3, 2, 1, and there's 40 different ways you can get a 3, 1, 1, 1, right? And then from that, I was able to find my mistake. Of course, it was a silly mistake, but still a mistake. And that's it. So, but now you can do this for different k's. So let's do k equals 4. And when n equals 6 and k equals 4, there's 90 orderings of a loop of 4 and 2, and then there's 90 of 4, 1, 1. Let's do it for 2. And that's it. These are the different types of loop orderings. Let's run it for 7 just to see. I don't know how long this is going to take, but let's run it. And then let's figure it out for, say, 3. So this is it. This is the exact number of possible loops with maximum of, whatever this number is. So we're going to run it for 3. Now let's run it for 4 since there's a lot of possibilities there. Now I want to know the specific types of orderings that have a maximum of 4. So I run this piece of code, and actually I could probably run this once and then generate these again, but I didn't do it. That's why they're so inefficient. And this is it. There's 420 ways you can get a loop of 4 and a loop of 3. 630 ways you can get a loop of 4, 2, and 1. And then 210 to get a 4, 1, 1. Anyway, I just think it ended up being a neat little piece of code that helped me understand the problem. And that's all I have for this video. Hopefully you enjoyed that, because I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.